Hi everybody, welcome back. This is Chapter 11, Lesson 3 for AP Chemistry. And in this section, this deals with Section 11.3, and we're going to be dealing with factors that affect whether or not something dissolves. So in your notes under number 1, it says one factor that affects solubility, and that is structure. Structure affects solubility because structure determines polarity, and polarity determines solubility. Oops. So to demonstrate this concept that structure determines polarity, what you have here in your notes is also the same diagram as figure 11.4 in your textbook. This first vitamin here, this is vitamin A. And the big atoms here are carbon, and the little guys are hydrogen. So this is mostly like a lot of carbon and hydrogen nonpolar groups with one little oxygen bond. There's a couple hydrogens bonded there, but one little oxygen bonded to the carbon. So it's mostly nonpolar groups. And so this is a nonpolar molecule largely, and it is soluble in nonpolar substances like fat. So this is a fat-soluble vitamin. And what that means is your body can store vitamin A. And actually you could overdose on it because it can store it. It doesn't come out in your urine. This is vitamin C over here. And vitamin C, you can see, has more oxygen to hydrogen groups. It's more polar. So this is not stored in your fat. And it will actually come out in your urine. It'll come out in water in your urine. So it's really not possible to overdose on vitamin C, though it is possible to overdose on vitamin A, and that's due to their structure, which determines their polarity, which determines whether or not they dissolve in water or in your urine, or they can be dissolved in your fat and stored in your fat. That's the difference in those vitamins. So structure certainly determines polarity, which determines solubility. Another thing that affects solubility is pressure, and I think there's a couple things that we're missing there, right, in our notes before we get on to pressure. It says one important factor in water solubility is the ratio of polar to nonpolar groups. Okay? And the higher the ratio, the more likely the substance is to be soluble in water. And that's basically what we just talked about with the vitamin thing. Another factor that affects solubility is pressure, but pressure only affects the solubility of a gas. Okay? It has little effect on a substance in either the solid or aqueous phases, or liquid. It only affects solubility of a gas. Okay? Carbonated beverages are, that's what this picture is showing you. Carbonated beverages are actually bottled at high pressures so that you force the carbon dioxide in. So in this diagram here, you'll see there's low pressure on the gas. You're not smushing the gas. The pressure is very low. If you decrease the volume, you increase the pressure. And if you increase the pressure, you force more gas into solution. So next to the picture of your soda pop, it says carbonated beverages are bottled at high pressures to ensure a high concentration of carbon dioxide in the liquid. High pressure increases the solubility of a gas. So gases are more soluble under conditions of high pressure. And I want to show you this little video because this is actually a law in chemistry. It's called Henry's Law, and it describes quantitatively the effect of pressure on concentration. So let me show you this quick little video. Hopefully it'll work, a video within a video. We'll see. I have to move this over a little bit.
The solubility of a gas in any solvent is proportional to the pressure of the gas over the liquid. Here we see a gas in equilibrium between the liquid and gas phases. When the gas is compressed, the solubility of the gas in the liquid phase increases in proportion to the increased pressure. The relationship between gas pressure and solubility is known as Henry's Law.
So this relationship between how much gas is dissolved and the pressure on the surface of the liquid is known as Henry's Law. And what it says in words is the concentration of a gas in solution varies directly. So that word that goes in that blank is directly with the pressure exerted on a gas. So the equation for Henry's Law, according to your textbook, is given as C equals Kp. And we'll define these variables. P is the pressure on the gas or of the solution. Okay. That's going to be measured in atmospheres. Or we abbreviate that ATM. K is a constant, and it's a constant for a given substance. What is it called? It's called it's called a constant characteristic of a particular solution, okay? And the units for that constant are moles over liter atmospheres. So it's a constant for a substance. They will either give that to you or they'll ask you to find that and give you the other two pieces of information. And then C is molarity or concentration, and its units are moles per liter. So hopefully you can see that if the pressure is higher, then the concentration is of gas in solution is greater. So that's what this concentration is. It's the concentration of gas in solution. So if you take a look at the next page, there's a typical question there that you might run into. A certain soft drink is bottled so that a bottle at 25 degrees contains carbon dioxide at a pressure of 5 atmospheres. So when we're at 25 degrees Celsius and a pressure of 5 atmospheres, that's 5 times the pressure that we're at right now. We're at about 1 atmosphere. So the pressure is 5 atmospheres over the liquid. Assuming the partial pressure of carbon dioxide in the atmosphere is 4 times 10 to the 4th atm, calculate the equilibrium concentrations of CO2 in the soda before and after the bottle is opened. The Henry's Law constant for CO2 in aqueous solution is 3.1 times 10 to the negative 2 moles per liter atmosphere. So this is the constant for CO2. This is the pressure when you bottle it. If we're at 25 degrees, so that's when it's closed, right? When the bottle's closed. When you open the bottle, then the pressure becomes equal to the pressure in the air. And the pressure of carbon dioxide in the air is 4 times 10 to the negative 4th atmospheres, obviously much lower. The constant is the same for carbon dioxide, 3.1 times 10 to the negative 2 moles per liter atmospheres. So what they're asking us is the concentration of CO2 in that solution when the lid's on, and the concentration of CO2 in that solution when the bottle's open. So we're going to do 2 separate calculations here, right? C equals Kp, C equals K, which is 3.1 times 10 to the negative 2 moles over liter atmospheres times 5 atmospheres. And that will give us our concentration when the top is on our soda. So if we take 3.1 to the EE negative 2 and we multiply it by 5, you get our concentration of 0.155. The atmospheres cancel out, moles per liter. That's a concentration of carbon dioxide in a bottle of soda, okay? If you calculate the concentration over here, you're going to have 3.1 times 10 to the negative 2 times 4 times 10 to the negative 4th. And you get 1.24 times 10 to the negative 5 moles per liter. So the reason you get the whoosh when you open your soda is that you actually decrease the pressure and the carbon dioxide comes out of solution and the concentration goes down quite a bit. Okay? That's Henry's law. The higher the pressure, the greater the concentration. The lower the pressure, the lower the concentration. Okay? Another factor that affects solubility is temperature. Temperature effect depends on whether or not you have a solid or gas. Solids in general, as you increase the temperature, you increase the solubility. So the solubility of most solids in water increases with an increase in temperature. You can dissolve more sugar in hot water than you can in cold water, etc. Okay? So the solubility of most solids increases with increasing temperature. So another factor that affects solubility is temperature. Some important exceptions are the sodium sulfate and the cerium sulfate. I think you don't have to memorize those exceptions anymore. With gases, the trend is opposite. Gases are more soluble when it's cold. So the solubility of most gases in water decreases with increasing temperature. As it gets hotter, you can dissolve, you can see less oxygen, less carbon monoxide, less methane, less everything. Okay? So the solubility of most solids increases with increasing temperature. The rate at which solids dissolve increases when you increase the salt surface area. So if you grind it up into a small particle size, it will dissolve faster. The solubility of gases decreases with increasing temperature. And when you increase the pressure above a gas, you actually increase its solubility. Okay. Okay. So just to summarize, solids dissolve best when you're at high temp and high surface area. Gases dissolve best when you're at low temp and high pressure. Okay? And then finally, reviewing from last year, we can use solubility curves. And if you've dissolved the maximum amount you can, we refer to you as saturated. If you dissolve less than you can, you are unsaturated. And more, you are supersaturated.